Yeah, thank you for the introduction, and thank you Boomedian for organizing this great workshop. And my name is Yuka Hashimoto from NTT, and it's Japanese telecommunication company. So today I'd like to talk about Koopman-based generalization bound. So we would like to apply Koopman operators to analyzing neural networks. And we especially focus on the generalization property of the neural networks. Yeah. So this is the agenda of this talk. And we first begin by the motivation and background, and then we will go into the technical part, and then we will show some numerical results. So in this talk, we consider a function, we consider a neural network like equation number 1, like this. So here, W1 is a linear transformation, and BJ is the bias, it is the shift operator, and sigma j is the activation function, nonlinear activation function, and G is the final nonlinear transformation. And we consider the composition of these operators and functions. And we first consider the action of W1. It is also called the weight matrix. And we first act this operator on the input vector, and then we act the bias, and then we consider the activation function. And then we continue that. And finally, we get the output. And we consider representing this neural network by using the Koopman operators. And the definition of the Koopman operator is already introduced by Igor, so I skipped the definition. But in this talk, we focus on the Koopman operator on the Sobolev space. So I will explain in detail in the next slide, but we are considering the space of functions with smooth functions. And by using these Koopman operators, we can represent the neural network like we can represent this composition structure by using the Koopman operators. And as a result, we get the equation number 3 like this. So in this case, we first have a nonlinear transformation G here, and then we apply the Koopman operator. And this is the Koopman operator for the final layer. And then we continue, and then finally we consider the action of the Koopman operator with respect to the first layer. And then we can get the whole neural network. And since the composition structure is represented by the product of the Koopman operators, we can easily split the behavior of each layer, so by splitting the product like this. So our goal is to analyze the composition structure of neural networks, especially the generalization property with Koopman operators. So let me briefly explain the Sobolev space and why we consider the Sobolev space. So here, we consider the Sobolev space like this, and here Sj is the order of the smoothness. And in this Sobolev space, the inner product is defined by using the Fourier transform and the integration like this. And if the function is sufficiently smooth with respect to the dimension dj here, then the Sobolev space is a reproducing kernel Hilbert space. So it is abbreviated by RKHS. So I skip the detailed definition and the detailed explanation of RKHS, but the important property here is the reproducing property. So it is if we consider the inner product between the kernel function evaluated at x and a function f in the Sobolev space, then we can reproduce the value of f at x. So by using this reproducing property, we can use this property to bounding the generalization error. So I will explain briefly later. And in this talk, we focus on the generalization property. Now, generalization means how much does the model predict well on unseen data, not training data. And one typical way for bounding the generalization error, or evaluating the generalization property, is bounding the Rademacher complexity. So since the generalization error is bounded by the Rademacher complexity, bounding Rademacher complexity means bounding the generalization error. The Rademacher complexity is the measure of the complexity of the model, and it is defined as follows. So let omega be a probability space, and let x1 up to xn be given data, and let f be a function class, and let s1 up to sn be the Rademacher IID Rademacher variables. That is the probability of, so S1 takes its value at 1 and minus 1 with the same probability. So the Rademacher variables changes, the value of the Rademacher variable changes 1 and minus 1 between 1 and minus 1 arbitrarily. So if f is sufficiently complicated, then the value of f can also change it between minus 1 and 1, minus and plus. And so if we consider this product, then this product can become positive. And if f is sufficiently complex, this Rademacher complexity becomes large. And this is a figure for explaining the generalization and the Rademacher complexity. Here we are considering the classification task, and we want to split the blue part and the red part. And the black line corresponds to the function f here. So by choosing a proper f, we want to split the blue part and red part. And in the left case, this function is very simple. And in this case, the generalization property is good, generalization is good, and the Rademacher complexity is small because this function is very simple. And in this case, the generalization error is small. On the other hand, in the right case, in this case, this function f can perfectly split the blue part and red part in this setting. But if we have new data here, if we have a new blue data like here, then this function fails to classify blue part and red part. So it means that the generalization property is not good. So in this case, the generalization is not good, but Rademacher complexity, this function is very complicated. So Rademacher complexity is large, and the generalization error is also large. So we consider this program for neural networks. And there are many existing works for evaluating generalization errors. And they are typical ones. And we skipped the detailed notation here, but an important fact here is that we have the Frobenius norm of the weight matrix here in the numerator of the bound. So it means if the weight matrix has small singular values, then the bound becomes small. And also we have another type of neural networks generalization bounds. And here Rj tilde is the rank of the weight matrix. So this type of bound means if the rank of the weight matrix is small, then the bound becomes small. The generalization error becomes small. So in summary, if the singular values of the weight matrices are small or the ranks of the weight matrices are low, then the bounds are small for existing bounds. So here our question is that, so we know what happens if the weight matrices are low rank or have small singular values, but what happens if the weight matrices are high rank? So empirically, there are some existing results that shows high rank, the neural networks with high rank weight matrices also generalize well. But it was not fully understood theoretically. So our goal is that we want to analyze the generalization property of neural networks with high rank weight matrices by using Koopman operators. And we get the theorem number 1 as an answer of this question. So here the left-hand side is the Rademacher complexity. So it is something like the generalization error. And the right-hand side is obtained by using the Koopman operators. And the important fact here is that the interesting part is the red part. And we have the determinant of the weight matrices in the denominator of the bound. And this determinant term is coming from the Koopman operators. And it means that even if the weight matrices have small singular values, large singular values, it can also become small. Yeah. So here is some remarks regarding this bound. So if the weight matrices are unitary, so unitary matrices are typical examples of full rank matrices. So in existing works, they don't focus on this type of full rank matrices. But using this, our bound, we can know that if the weight matrices are unitary, then the network generalizes well. Because if Wj is unitary, then the red part becomes 1. So it is the smallest value of this bound. And also, as I said, a bound can become small even if the weight matrix has large singular values. And I will explain in detail later, but a bound is suitable for lower layers. It means the layers near the input. So because our bound is suitable for unitary operator, it is something like the rotation. So we can interpret that the input signal is transformed by the unitary operators, like rotation, and then the signal is extracted by the higher layers. And our bound is suitable for the lower layers. And this is the proof of our theorem. I skipped the detail, but the important part is here. Since we are considering the Sobolev space, the norm of the function is defined by using the Fourier transformation. And if we consider the composition of the linear operator, so linear weight matrix, we have like this. And we have Wj here. So we can apply the change of the variables form, and then we can get the determinant term here. Yeah, so this is the proof that I will skip. Yeah. So we have a Koopman-based bound like this, but it is a little problematic because we have the determinant term here. It is very good, but if Wj is not injective, then this term becomes 0 and the bound goes to infinity. So we want to extend our bound for non-injective weight matrices. And for this purpose, we have two approaches. The one is the graph-based one, and the second one is the weighted Koopman-based one. And as we will see, if we modify the neural network slightly, then we can apply these approaches, and we can get a similar bound for at the neural network with injective weight matrices. So first, we explain graph-based approach. So instead of the original weight matrix Wj, we consider this type of injective operator. And here, Pj is the orthogonal projection onto the kernel of the weight matrix. And we consider Bj tilde and sigma j tilde and g tilde like this. And here, psi is a function which decays, and it takes its value at 1 at the center of the domain, like this. So psi is like the form, psi is form like this. And by using these functions and operators, we have a slightly modified neural network, F tilde, like equation number 6. So we have two parts, and the red part is the original neural network. And we also have the psi function here, but psi is like this form. So if the data is at the center of the domain of G, then the neural network is the modified neural network F tilde, and the original neural network is the same at the center of the domain. So by using this modified neural network, we can derive a similar bound as the case of the injective weight matrices. Here, instead of the determinant of Wj, we have the determinant of the sum of the identity matrix and the Wj star and Wj. So it is also applied to, we can also apply this bound to non-injective weight matrices. Yeah, but we have also, still we have determinant term here. So it means even if the singular value of Wj is large, the bound becomes small. Yeah, we can also use weighted Koopman operator for tackle this program. And here we also consider a function decays in the direction of the kernel of the weight matrix. And we consider the Koopman operator and the multiplication of this function. So this is called the weighted Koopman operator. And using this weighted Koopman operator, we can construct a similar, the same modified neural network as the case of the graph-based approach. And we can get a similar result as the case of the graph-based approach. We still have the determinant term here. And yeah, we got a Koopman-based generalization bound, but our bound can be combined with existing bounds. And here, this is our result. So this part is our Koopman-based bound, and it can be applied to the lower layers. So because J is small here, and we can also apply the existing approach to get this part. And this is for higher layers. So technically, we can, we skip the proof, but technically, we can apply our Koopman operator bound to the lower layers. So it justifies the interpretation I explained here. So our bound is suitable for lower layers, and technically, we can also show our bound is suitable for the lower layers. So we finally show some numerical results. So first, we consider a classification task of the MNIST. So here, the vertical axis represents the test accuracy of the classification. So the higher is the better. And the orange line is the result with regularization based on our Koopman bound. So we try to minimize the loss function, but simultaneously, we try to minimize this term. So this term. So for training the neural networks, we apply some method like SGD or Adams, some optimization methods. And by using these optimization methods, we minimize the loss function and the red term here. So this means the regularization. And this orange line is the result with the regularization based on the Koopman operator bound. And the blue line is the standard optimization without the regularization. And we can see that with the regularization, we get high accuracy for test data. So it means that if we try to minimize our bounds, then the neural networks generalize well. And this is another numerical result. And so here, the vertical axis represents the condition number of the weight matrix. And the orange line corresponds to the second layer, the behavior of the weight matrix of the second layer. And the blue line is the third layer, and red is the fourth, and the green is the fifth. And we can see that for the second layer, as the learning process proceeds, the condition number becomes small. And our bound becomes small if the condition number is small. So it means our bound is suitable for the second layer, the lower layer. On the other hand, the red and blue line shows the condition number becomes large as the learning process proceeds. And it means the existing result is suitable for these layers. So because for existing results, if the condition number is large, then the existing bound becomes small. So we can see by this result, we can see that the behavior of the layers are different between the lower layers and the higher layers. And our bound is suitable for lower layers. So we also empirically confirmed this. This is a theoretical part, but we can also confirm empirically like this. So in conclusion, we derived a generalization bound using Koopman operators. And if the weight matrices are unitary, then the the bound becomes small, and our bound sets light on the generalization property of neural networks with high rank weight matrices. So it is not fully understood by existing results. So for future work, we consider a more general setting, and also we have to consider the bound of the Koopman operator for activation functions. I think, yeah, that's all, and thank you for listening.